Yeah, thanks for the introduction. My name is Daniel Greve from Münster University, and I work together with Tobias Frau-Filzmann, my predecessor, and my supervisor, Uwe Thiele, on the so-called non-reciprocal Cahn-Hilliard model. I will soon introduce that. And we derived an analytical Maxwell construction for that. And I hope I can convince you that this is kind of interesting. Okay, let's start. So this kind of continues with the work that Adrian presented and also Jon Dunkel. And so the only difference is that we still work with active matter, but we do consider scalar fields. And we also do not consider inertia. And so if you've got a model which behaves thermodynamically or passive, then you come up with a theory of the left. So this is a very old idea by Onsager and Gibbs. So this is well known. That if you've got many scalar order parameters, let's say concentration fields or something, and they are driven by this thermodynamic functional like a free energy, then you can write down such a theory, which means that the free energy variation, the gradient of this gives you a thermodynamic force, and then you multiply with a positive definite Onsager matrix, and the divergence of this flux then gives you the local change of the concentrations. And this is very important consequences for these kind of theories. So everything is thermodynamically consistent, and therefore the energy has to decrease. And what's also interesting is that then you can always do a Maxwell construction. So you can talk about phase coexistence in a very canonical way. And examples for these models are Cahn-Hilliard models or thin film models or phase field crystal models. So there are various models that you can write down once you know the energy. Yeah.
These are all for conserved order parameter, right?
Yeah, this is exactly. So this is what I wanted to say next. So here we only consider conserved order parameters. If you don't have conserved order parameter, you just have this functional variation and the mobility. So then you don't have a flux proportional, but just this term instantly. But for this Maxwell construction, it is important that we have this at least one conserved order parameters, and here for simplicity I only consider conserved order parameter. On the other hand, we have active mixtures, so biological and chemical systems, and I think it's quite interesting to stand at the Newton Institute and tell you that there is Newton's third law is usually broken in biology and chemical systems. So you very often have on microscopic scales, so for your agents you have non-reciprocal interactions, which means like predator-prey dynamics. So a wolf hunting sheep and the sheep running away from the wolf. So this is non-reciprocal. And in biology you kind of see this across all scales. And therefore we know that there is no pair potential for the agents, and therefore if we derive PDE models or these field theories for active mixtures, we won't arrive at a theory which we can put here in the left, but with something else. So also PDE model in an overdamped limit, but it can't be put in this, this formalism. So therefore, one might stop and think, so this is impossible. But there's a class of systems which we call spurious gradient dynamics, which lives in between. So they show this active behavior which we want to describe, but they also allow for a Maxwell construction, which we can give analytically. And this is, for us, interesting. Okay, brief review on what the Maxwell construction is. So this is the Cahn-Hilliard model. It's kind of the simplest anti-diffusive model that you can write down, because here you allow for the diffusion coefficient to become negative. So you allow for phase separation, and then you stabilize for small wavelengths with this higher order gradient, and for large fields with this nonlinearity. And then you get like phase separation, and most of you will know this, so this has an underlying energy functional, and this penalizes gradients or interfaces, and therefore you come up, so in the final state you will end up with some phase separated state where you've got one phase of large concentration and one phase of small concentration. And then you want to know, how can I derive the concentrations in these phases? And this is what the Maxwell construction does. So you assume a setting like this, where you've got two phases which are connected by a boundary. And then, by a very old idea of Maxwell, you can derive that these phases have to share equal chemical potentials and equal pressure. So chemical potential is the derivative of your energy density, and the pressure is something like the negative grand potential. And As said, Maxwell already knew this, so you can draw such a picture. So here different thermodynamic variables, but the idea is the same, and therefore you can see that the coexisting densities are governed by an equal area construction, or equivalently, if you integrate this once along the u-axis, you come up with this double tangent construction. So this is equivalent, and this is both what we call the Maxwell construction. This is not exclusive to this Cahn-Hilliard type model, so you can basically do this for every model which has this gradient dynamic structure. So this is important. Okay, so this is kind of well known. This is the Cahn-Hilliard model. So next I want to introduce to you the non-reciprocal Cahn-Hilliard model. So we start with the ordinary Cahn-Hilliard model. Then we just clone the fields. So we have two scalar fields, like two concentration fields. And for the second one, this is important. We also introduce this rigidity, which means that both fields can be in a, so if you have the non-conserved equivalent, that would be like in a Turing system that they can diffuse differently. And then we introduce interactions. So we introduce one reciprocal interaction, so both are linear, and this rho means that both species tend to attract or attract each other, or if the sign is negative, they want to be separated. And on the other hand, alpha is our non-reciprocal interaction. So this is really where the system becomes active, because alpha says one species chases after the other, but the other tries to run away. And so this model has been introduced from different angles. So first by groups who just postulated it on phenomenological considerations. Lately, we've got a macroscopic derivation for so-called run-tumbling particles. And it's also, if you come from the macroscopic scale and just go for symmetries and so on, you can also derive a model with more complicated parameters, but the same structure as the leading order amplitude equation. Okay, so there's a lot of going on in these models. So compared to the Cahn-Hilliard model, where you can have just phase separation, you can have like traveling waves in 1D, 2D, you can have like traveling structures. You can even see chaos if you go to Neumann boundary conditions. And if you set kappa unequal to 1, you get the same mechanism as the Turing mechanism, but just for the conserved case. So then you get like localized snaking and various mechanisms where coarsening is suppressed. So where you don't go to a structure that has the extent of your system, but maybe too periodic or have another periodicity. Okay, so now we want to bring a bit more structure into all these phenomena. So we want to explore the parameter space, and to do that we use the standard tool of nonlinear physics, so or nonlinear dynamics, and use linear stability analysis. And therefore we have three different instabilities in this non-reciprocal Cahn-Hilliard model, depending on where we are in the parameter space. The one is well known, the Cahn-Hilliard instability, so one large scale instability with real eigenvalue. Then we've got conserved Hopf instability, also large-scale instability, but with two complex conjugated complex eigenvalues. And we have got, as I said, this equivalent of a Turing mechanism, where we have this small-scale eigenvalue, but in the conserved case. And the latter two require non-reciprocity. So you really can only get them if you have got dominant non-reciprocity in your model. So this parameter theta greater than 0 means that non-reciprocity is a dominant contribution in your model. Okay, and then we are interested in phase diagrams. So our Maxwell construction finally should give us phase diagrams, and therefore we are interested in SPI nodals, so linear stability thresholds for our system. And as the fields are conserved, the average concentrations U1 and U2 are good parameters, so we try to derive the phase diagrams in these composition planes. And from left to right, I increase the non-reciprocity. What you can see is, on the one hand, that we get this kernel of oscillatory instability in the center. So in the center, the nonlinearities are not important, but really it's the non-reciprocal coupling which is important. And therefore there you get this blue circle. And on the other hand, if you, as I said, if you put kappa equal to 20 or something unequal to 1, you get this Turing instability stripes that you can also have in this model. So once you go to non-reciprocity dominating, you can have three different instabilities. Okay, so this is the SPI nodals, and next we want to talk about phase coexistence. So we want to derive the coexisting densities in coexisting phases. And therefore, So this is a trick that, in my eyes, it was kind of a magic trick when I first saw it. So my predecessor, Tobias, came up with it, and he found that you can parameterize this model differently. So you can factor out the interaction, and it goes like this. So from here to here, you factor out this factor rho plus alpha over rho and rho minus alpha over rho. And all of a sudden, it looks like your two fields are coupled reciprocally. So you have a factor rho in both equations and have this scalings of your single particle energies. So this second structure all of a sudden looks like a gradient dynamics, and you can bring it into this structure. So you can rewrite these equations as this system. So you might ask yourself, so have we now mapped this non-reciprocal interacting system onto a reciprocal one? Does it make sense? The answer is yes, but it comes with a trade-off, because you have this matrix M and this energy functional F, and if alpha becomes greater than rho, so if your non-reciprocity dominates, then M is no longer positive definite and F is not bounded from below. So your energy has some kind of weird hyperbolic shape, your M is indefinite, and therefore you don't have this idea of a decreasing energy, but otherwise, on a superficial level, you can still do a Maxwell construction, and that's what we did. So this still gives you coexistence conditions for coexisting phases. Okay, and then we just took this coexistence condition and constructed the binodals. So we have two chemical potentials and one pressure, and therefore we can find these lines in the average composition plane. So there's a lot to explore here, and so what's interesting is, so they kind of follow this binodals. So once you increase the non-reciprocity, the binodals retreat from the center of the phase diagram where the activity really plays a role. And on the other hand, you get additional things like these coexistences between crystal and uniform phase, or these binodal lines where one phase is stable and the other is Hopf unstable. So one does not really understand what happens there if one does not look at a finite system. Therefore, for the remainder of my talk, I want to show you what happens in the finite size equivalent. So especially for this binodal here in C that is marked, and this one in D. And I will start with the one in D. Okay, D is a binodal for crystallization. So you walk along this binodal line. And what you can then see is, if you plot your energy and all the localized states you get like snaking, like in a phase field crystal model, so you get these localized states. And if you order them by the extrema of the energy and then arrange them in the pressure plane, they perfectly align with the Maxwell plane, with the Maxwell line. So the whole message here is, despite this crystalline state only occurring because of your non-reciprocity, this Maxwell line fully explains the crystalline states that you see here. And of course, you can also do that in 2D. So here in the middle, I just put this unstable phase, so which does crystallization, and on the outer side, I put the stable phase. And then if you start, you can see that this model does crystallization like a phase field crystal model. So short wavelength instability, but with conserved fields. Okay, so here it's just the Maxwell construction fully gives you the information about the system, and you get this coexisting stationary state. On the other hand, now comes the really interesting binodal. So here you connect one state that is stable to a state that's Hopf unstable. So here it's unclear what will happen, because of course you won't have this state coexisting with this one, because this one will instantly destabilize and show some oscillation. Therefore, we do again continuation. So we walk along this binodal with our continuation parameter U1 bar. And what we then see is that we first get phase separated states like in the passive case. So like for the ordinary Cahn-Hilliard model. But then something interesting happens if they reach an extent of 12 pi. So these three green lines are different extents of the whole systems. But whenever the unstable domain reaches an extent of 12 pi, in this case, we see a secondary Hopf instability. And here you see this region enlarged. And then you can see that we see oscillatory states. So you find these localized oscillations. And at some point, all destabilize in secondary torus bifurcations, and you don't know what happens next. Therefore, we also do time simulations. So this is here in 1D. So first you see you get these simple oscillations that we can also see in bifurcation analysis, but then later on you get like quasi-periodic states and then even more complicated quasi-periodic states, and once it fills the whole domain, it kind of becomes chaotic. And what I want to show you last is that the same also happens in 2D. So here from top left to bottom right, I just put bigger domains of this unstable state, and then I run simulations. And you can see first it looks like it's a very regular oscillation in all cases, but then you see here on the top left, this dies out, and you end up with a stable state. And on the other hand, here on the bottom right, and here especially these three, this really becomes some kind of chaotic wobbling around phase. But nevertheless, it's still more or less confined to the regime which is predicted by our Maxwell construction. And also, if you plot the averages, they are more or less good described by this Maxwell construction, by the spurious Maxwell construction. Okay, if you go to larger phases, so these are more or less small domains, and if I go to larger phases, so here I plot both fields and not only one, then you can more or less see the same behavior. And here I waited a long time so 10 to the 4 to separate the initial transient, and then in the end you will end up with some state like this. So you get an inner phase where you've got these oscillations and these predator-prey dynamics, and on the other hand, on the outside you still have coexistence with this stable state. And what's also quite interesting, I think, is that you have these enclosures of the stable phase, which you don't see in passive phase separations. So this would be an interesting avenue. So you can also see them in comparable models like active model B+, but here I think we do not understand much about them so far. Okay, with this let me conclude. So you can derive this Maxwell construction for a non-reciprocal Cahn-Hilliard model that explains the coexistences of stationary states, and even for this crystalline states, which only occur if you got this predator-prey interaction types. And despite this has to break down if you have oscillations, so then you can no longer set the left-hand side of your equation to 0 and do a Maxwell construction. But nevertheless, this construction seems to predict this localized oscillatory phases, which only occur if you have non-reciprocal interactions. With this, thank you for your attention, and then I'm open for questions. Yes?
If you start with, in these models, if you start with a well-mixed state, then do you see growth laws and things like that?
So it really depends on where you are in your composition plane. So if you look at the phase diagrams, it's kind of, if you like start here, you get like first spinal decomposition because you're in an unstable regime. But in general, multi-stability is really a thing. So you can start with a state where one phase is unstable and the other is stable, but the overall average composition can also be stable. So this is not clear from just So as an example for this, if I start with the average composition in the white space, obviously nothing will happen. But if I go to the orange regime, so where I'm unstable, then I will see crystallization. So it's like, yeah. Yes.
So in the bubbles you showed at the last slide, can you think of the lack of coarsening in the interior as some kind of competition between tendency to coarsen and the dynamics in the background?
So the short answer is, so no, here I don't understand this, but in general I think there's really a difference between phase separation in the stationary case and in the oscillatory case. So even in simpler things where you just have traveling waves, coarsening is really usually suppressed if you've got traveling waves instead of like the stationary Cahn-Hilliard model. So I think there are more length scales at work that we don't understand right now, probably. But so this is the short answer is no. I don't know yet.
Further question? Well, let's thank Daniel very much again.
Thank you.